people. Any questions about anything? Any clarification questions about the homework? Perfect. I think that next meeting we'll play a bit with active learning, play a bit with either hashing, stable marriage, skip list, all of it. So try to get to make a quick pick at the material before you're joining us. Okay, and we're moving to a new topic, hashing, which I'm aware that you have seen it in data structures, definitely, and I'll try to tell you things that will add to what you have seen before, as well as hashing is such a fundamental and so important data structure that I don't feel too bad even if I repeat things that you already know. I'll try not to overwaste time about it. And I want to tell you about hashing, and for this I want to tell you about the way that in my undergrads way back good 30 years ago, that's how graded homeworks were returned to the students. So we were giving our homeworks, properly handwritten or printed on, but on papers. And then the graders and the TA were writing comments about these homeworks, and then we would go and pick the graded homeworks. And the way that we pick the homeworks were to go to one particular room at which we had a cubby for homework returning, you know, kind of a wooden closet with 100 cells. And these cells were labeled. We had cell 00, cell 01, cell 02, and so on, all the way up to, in the first row, it was all the way up to cell 09, and altogether all the way up to cells 99. And the way it went was that the grader was coming with a bunch of homeworks. On each homework, the student ID appeared. And if your ID was ended with 99, then the grader would have put the homework right here. So that was where they'll pick your homework with grade 99. If your ID was ended by the, if your ID was say 1, 2, 3, 4, 5, 0, 1, then of course that's where you'd find your homework. And this method was working very well. And the reason that it worked so well, at least in terms of the time to put the homeworks all in place and the time to pick your own homework, the reason that this method works so well was because of the same principle that hashing works so well as a data structure. So let's play a bit with math. So let's assume that we will have, say, 5 courses. 5 courses, each with 100 students, making us that at each moment we had about 500 homeworks that we had to put in this one cubby. Okay, just an estimation. So we had 500 homeworks to place in all these cubbies. There was one cubby for all the homeworks. Side comment, of course, privacy was not an issue here. There was no, you could have seen other people's homeworks, so that is not something we discussed here. So we are having 500 homeworks altogether, which means what? You would have gone to pick your homework your own homework, to find the cell that returns your own homework, you know what's your ID. You know that your ID, say, ended up by 01. So getting to the cell that contains your graded homework was quite easy. However, in this homework, you would have find others people homework as well. Oh, but obviously there were other homeworks together with your own homework in the very same cell, and you had to pick the whole stack of homeworks and identify your very own homework out of this batch. So theoretically, you might have needed to check 500 homeworks of each and every student in each and every course together, which were all mixed in the same cell. Theoretically, it's possible. Theoretically, it's possible that all the student ID were ended all with 01, and the method would have failed miserably. But a more reasonable assumption is, what is the average number of homework per cell? Well, if we have 500 homeworks and we have 100 cells, we're getting that the average number is 5 homeworks per each cell. Make sense? So does it mean that every cell had exactly 500 homework, has exactly 5 homeworks? That's of course very far from the truth. Definitely some cells were empty. Some cells contains more than only 5 homeworks, and they expected 5 homeworks. However, you would ask, what is the probability that if the way that the student ID are given to students, if this method was random enough, then how many homeworks, how many students will have that will end with the same ID? Well, you'd expect that you'll be, it's too optimistic to think that in every set of 100 students there will be only one student with the same ID, because the way that ID was assigned has nothing to do with who is in the course with me. However, it will make sense to assume that I will not have more than 3 or 4 or 5 other students with the same ID with me. So in this aspect, this method worked out very well. So it's the same assumption that will escort us with all the homeworks. It's very rare that we have an exact uniform distribution, exactly one homework per cell, but it's rare that we are very far away from the average. Again, it is unlikely that we will be diverging from the average by a lot of by a large number. Okay. So once again, like in the skip list, the average is close enough the average is close enough to what we see in the real life under the experiments. Okay, and we will use this example a few times when I'll talk about hashing. I really like this example. So I'll talk about hashing, follow part of the time the book by the CLRS, and some of the slides are actually was given from the authors, from Charles Lyserson to be precise, so thanks. But I'll also speak more about application of hashing beyond data structure, and in this part I'll use other sources. Okay, so we'll see many more applications for hashing beyond data structures only. I think that we already went through the question, what is hashing? Remember where the word is coming from? Hashing is coming from this operation of cooking, of taking taking some meat and chopping it and scramble it and essentially sprinkle it all over, so it will look like it is uniformly distributed, which is exactly the same assumptions that we are doing right here in the homework, where we hope that the ways that the homeworks will be assigned to the cells in terms of how many homeworks we'll find in each cell, it will be as if we are uniformly sprinkled the homeworks in the cell, and every cell has the same probability to contain each one with the homeworks. Right. So when we are talking about hashing in general, we'll assume that that we have items of data, records, and in every record we have the key and some auxiliary data, satellite data, everything else that goes with the keys. So every time I'll say here is a key of something, always assume there is some amount of data associated with this and stored together or stored elsewhere. We don't know. And we need a data structure that will support the three basic operations: insert of a new record based on the ID, delete, and search. And how should this data structure T was organized? Well, we'll use our cubby as before. Here is an example of the cubby, just smaller. Set numbers to each one of the cells, 0, 1, 2, 3, all the way up to, I have 8 cells over here. I'll always start counting at 0. First cell will start at 0. And I need, and we'll start immediately with formalization. So the little fuzzy feelings that you have that you understand everything will soon go away, because I'll kill it with enough many notation and formalization. I'm joking, it's not that bad, but there are a few notations that we have to go through. There is a universe, and the universe will contain every possible student ID that might appear. Every possible student ID that might appear, or for this purpose, or your own student IDs, we will talk about every number that has 16 many decimal digits. I think that's what student ID are consisting of, 16 many decimal digits. And what we expect from our hash function would be that as an input, this hash function can handle each one of these numbers. Remember, we don't know ahead of time who are the students that are at the university right now for which I'm building my data structure. Or I want to build a data structure for the students of next year, and I don't know who they will be. So I'll make the assumption that every number might appear as a student ID, and I want my hash function to be willing to accept this part of the input. If I'll start to use alphanumeric symbols, A, B, C, D, E, exclamation part, emojis as part of the inputs, then of course I need a different hash function that will be willing to take emojis as legit inputs. And this universe is, of course, enormous. There are a lot of numbers between 0 and 10 to the 16. And what I did in the next notation is, let's talk about the set, capital K. In the whole big chapter, we'll spend on hashing a lot of time. In the whole big chapter about hashing, capital K is a set of students that I need to store currently. These are already the set of students that are at the university right now, and it's not proportional. K is way, way smaller than the universe. And I need a hash function which is willing to take as an input every student ID and will spit out an index between 0 and M. M will be the number of cells in the cubby, the number of array in my cell. 8 in this example, 100, M is 100 in the example of the cubbies at the Technion. Okay, and what the hash function does is to take a key of a student, small k, an ID of existing student, and will decide to store his homework, his record at some point in the memory. That would be age of k1. So age is an index, a number between 0 and 99. And that's what I want my hash function to spit out. Where should I place my this student? Here is where I'll place a different student, age of k2. So age of k2 is the index of this student. k3 is the index of the third student. What is a hash function that we are using in the Kabi example over here? Help. What is a hash function that I'm using in this example? Help. It's truncation of the last two digit. If it's job interview and you want to impress everybody in how much math. I mean, if we think about k as a number, how do I get which mathematical operation gives me the last two digits?
You just do mod 100.
It will be k mod 100. Exactly. And we'll see the operation modulo a lot in this course, in this chapter. You'll know at the end much more about modulos than we want. That's an example of a hash function that worked well in this example. Of course, we will have to handle the case that collision happens, right? The set of universe and even the set k is usually much larger than the number of cells in the hash table or in the Kabi. So it will be an unavoidable the case that we'll have two students with the same ID. We'll have in the same cell several homeworks for the same ID. So collisions are not accidents, collisions in hash table. What happened when we have two keys, k1 and k2, that are mapped into the same cell. Collisions happens all the time. It's fine. We just need to handle them, and we need to see a few methods that will help us handle collisions. However, it will be completely unrealistic to expect that collisions don't happen at all. On the other hand, we would like to minimize the number of collisions. What happened here? What my search time is consisting of? My search time is when I'm going to pick my homework. My search time is consist of let's pick the batch of homeworks that are inside this cell, and now I need to go over each one of them and look for my very own. So the fewer collisions that I have, the fewer homework I have in the same cell, and the faster the search is. And it's easy to think about other hash functions that would work very badly. Right? If I'll pick, let's think about your own student ID. If I'll pick as age of k as the most significant two digit, but if I'll take from the number 1 to, if your student ID is 1, 2, 3, 4, 5, and I'll pick 1, 2 as your student ID, probably it would be a pretty bad hash function. Why? It will still split all the homeworks into all the cells, but if we think that the process of giving you IDs is based on running numerical numbers, 1, 2, 3, 4, 5, etc., then presumably all of you have the same first two digits. I'm making an assumption. I don't have any data that you don't. But I'll assume that there is very little variability with the first two digits, so probably most people in the class will be in one or in the same cell or one out of a few cells. The hash function will still work. It will still be completely legit. However, the time to find a homework here will be increased dramatically, because now I have to pick my own homework out of 500 other students that have collisions with me. So part of what I'll try to teach you in this chapter is how to pick good hash function and how to handle the case that your original guesstimate about what's good and what's bad is wrong and the hash function doesn't work the way you hope it to be. Okay, so a lot of the discussion would be how can I handle collisions. I have a few students that are mapped into the same cell. And the simplest way to handle collisions would be to resolve collisions by chaining. In computer data structure terms, what I'll do is that my hash table T does not store cells by itself, does not store record by itself, so I don't store the record of the student. Instead, I will store a pointer to a linked list of all the students that are mapped, whose ID mapped to index I. That is, both 49 and 86 and 52, all of them are mapped into this cell. So I'll just store a pointer to this linked list of records of these students. And notice that it's much less convenient already, right? Because if I'll go back one slide, then right now I can store, if I don't have collisions, it would be very convenient to store not only the student ID, but the whole student record in the table itself. So I save another access to the memory to retrieve the student record when I am bringing the student ID. It's much less convenient to store a linked list that forces me to go from here to that forces me to go to check from the table into the linked list and now check every element in the linked list. And besides, we prefer not to use pointers unless we absolutely have to, because it reduces our way to check the correctness of our program. It bother optimizations that runs on our code. It makes operation like paging between the memory, bringing pieces of the main memory into the hard drive and vice versa. All these paging and caching much less efficient. Pointers should be used only if necessary. But so resolving collision by chaining is an option. It has its pluses, it has its minuses, and it has a fair amount of minuses. How much an insert take if I'm resolving a collision by chaining? How much does an insert take? Warning, it's a trick question. Help? What's the worst case running time to insert a record into a hash table if I solve collision using chaining?
Would it be then if all the keys got mapped to one cell and you iterate all the way to the end of the last insert?
So it's very much depending on the policies that I'm using exactly of where I'm doing the insert. So it could be that the answer is O of n if I insist on inserting this element in the very last, and then I have to go through all the elements. Or I can say I'll insert a newcomer already at the beginning of the list, which will only take order 1. So insert, you can go either way. It can be order 1 or order n in the worst case, or at least the length of the list author. You can imagine that in my example with the cubbies, I'll always, if I'm the TA that puts a graded homework, I'll always put it on the top of the stack. So it will be order 1. Right? However, things are less nice when we are talking about search time. Search time, I have to go to the list of homeworks, go to the records that are linked together, and I have to check each one of them. And that's a time to introduce key terms that will come again and again through this chapter. I want to speak about the load factor of the table. So let n, the letter n will exclusively be used to tell me how many keys do I store in the table. How many homeworks do I have at the moment? N is always the number of keys in the table. M is always the number of slots in the table, 100 in this cubby. And the load factor, alpha, is a ratio between them, n over m. Number of keys divided by number of slots. And of course, we would like to keep this value as small as possible. No larger than 1 in some hash tables, or at least a constant in other hash tables. Right? Well, quick sanity check. What is the load factor here in the example that I just erased? I had 500 homeworks that I had to return, divided by, say, 100 cells. So alpha in this case was 5. Okay, what is therefore the search cost? Well, the expected, but now it's a very weak way of expected. It's expected only if the data is really friendly and distributed perfectly nicely. Then still the expected time to search for record will be 1, because you have to access the table no matter what, plus the length of the list of elements that you have to check. We had the table, we had a pointer that points to a linked list. What is the length of list? Right here, the average, in some sense, the average list will be how many elements do I store in the table altogether divided by how many cells do I have to store them. That would be the average number of homeworks per cell. So 1 plus alpha would be a reasonable bound in some sense. And that would be the expected search time. So as long as we keep alpha to be a constant, 5 in the example of the cubbies, maybe the search time is acceptable, is order 1, if alpha is order 1. Theta, I remind everybody, it's both order and omega. It's no more than this search time, and it's no less than that search time. So that would be the alpha. If alpha is a constant, then we are happy, and find still takes a constant time, which is of course as good as it can be. By the way, if I have k elements, say in the list, if I have in this list k keys, question, what is the average search? The average, and here I'll keep a word blank, the average search time. And the word that I keep here as blank might be successful or unsuccessful. Or successful or unsuccessful. Successful means I'm searching for a key that I know for sure that is one of the keys. So my search will end up by finding these keys. Unsuccessful will be I'm searching for a key that is not in the table. Which takes more time? Of course, unsuccessful takes more time because if it's a successful search, I have to look for only until I find the search. So if my search is unsuccessful, I have to check all the many keys in this list. What is my average time for a successful search? It's less than successful, but can you tell me how much is it?
Would that just be k over 2?
It will be k over 2, and the argument of why k over 2 is you can do the exact math, but the intuition is you're looking for one of these elements, one of the keys that you're looking for. Here is a green key that you're looking for. Let's look at the middle of the list. The chance that it is in the second half of the list is exactly the chance that it's in the first half of the list, if all permutations are equally likely. The probability that it's the last one is the same probability that it's the first one. The probability that it's the second is the same probability that it's one from the second, etc. So indeed, k half is the search time for the expected case. So the search over here will be for an unsuccessful search, the expected time is 1 plus alpha. For the successful search, it's 1 plus alpha half. In either case, the constant vanishes inside the theta, not more than O, but not less than omega. So that would be the search time. So the first take-home message from this is if you're using a table, try to keep it such that n, the number of keys, is no more than a constant times the number of cells of the table, implying that if you have more keys to store, you have to increase the size of the table proportionally. You want them always to be at the same order of magnitude. So what to do if this is not the case? What to do if I want to keep several hash together? I want to keep a lot of tables, and I don't, if I have only one table that I need to store everything inside this table, then I just use as much memory for it and I'm happy. I will not, then, as long as the number of slots m is larger than the number of keys, much larger is even better. The larger m is the larger m, the number of tables is, the fewer collisions you're going to have. What should you do if you don't enjoy this assumption of unlimited memory? For example, because you're planning to store a lot of hash tables, or you're using Arduino, or using some other tiny processor at which memory is much more scarce. How should I use a table in this case? Well, that's exactly where you're using dynamic arrays. And the idea is the following. You'll start using a hash table, which I'll take it completely to the extreme. You don't really start with a hash table of size 1, but just for the exercise, let's pretend that I'm using a hash table where I'll start where it is 1. Give me a sec. I want to see the chat if there is anything in the meantime. Okay, I don't see the chat. I'll pay attention. If somebody wants to tell me something, be vocal. So even if I'll go to the extreme, I'll assume that I start with just one cell, say. That's the size of the hash table. Once a key is inserted, I'll decide that I'll double the size of the hash table. Now, so I'll take a table twice as large, and I need to perform rehashing. Rehashing meaning I need a new hash table. Why I need a new hash table? Because my original hash table, we said the number that it spits is always between 1 and m. In the Kabi, it was always between 00 and 99. If I need a larger hash table, if I'm now using a hash table whose size is, I'm adding to it all the cells from 100 to 199, that is, makes the table twice as large, but my hash table is still only spitting out numbers in the range of 0 to 99, it means that all the cells in the new table will be empty and all this new memory will never be used. So I need to use a different hash function, which means take the cells from the original table and copy them into the new table using the new hash function, because presumably new hash function will place some of them in different locations. Okay, and now when this table is becoming full, then I'll double its size, taking a hash table of size 4 instead of 2, and again perform rehashing. Of course, rehashing is not when users are using the table. I'll tell everybody stop using the table for a few minutes, microseconds, whatever, and perform copy everything into the new table. And when this table is full, I'll allocate a table twice as large as the previous one, and so on and so forth. Each time you are doubling the size of the table. How much time do I spend for all these operations of keep doubling the table at each time? Well, if I copy, once I allocate a new table, I need to make sure that it doesn't contain garbage. All the cells are initialized to be 0 or something that is not left over from the previous program that was using the table. I need to copy elements from the previous table into the new table. Altogether it's linear, but it's linear in the size of the new table. So how much time does it take altogether? Well, if you just ended up with n keys, then the last operation, we are going back in history. We are start counting, but from the very last time that I doubled the size of the table. So I'm spending n time in the very last operation. How much time did I spend in the previous expansion of operation? It was half of n, because the table was half its size. Operation before that, it was quarter of n. Operation before that, it was eighth of n, and so on. Once again, the same mantra of the course. It's n times all these operations is at most 2n. So that's how you're doing. You're pretending that the table is dynamic, and notice that the average time that I need for all these operations is still linear. So the average time, what's called the amortized time per each insert, is still constant time, because it's n or 2n for the whole operation divided by n keys that I was inserting. So it's true that one operation, one insert might take n by itself because I just had to expand the table, but on average it's constant time per one insertion because I'm only spending 2n time for the whole series of operations. Okay, and you have a few variants of this exercise in the homeworks, by the way. Cool with everybody how we are using dynamic tables rather than a static one. So this exercise saves us the headache of deciding ahead of time what is exactly the size of the table. We can think that let's start with a relatively small table, and once we need to, we are just doubling its size and performing rehashing, and that's fine. The one big no-no to do is if you are performing a rehashing and reallocating of a new array, make the new array significantly larger than the previous one. Again, the new array should be significantly larger by a multiplicative constant, larger than the previous one. As I'm asking you in the homework to show that an exercise that will say I'm spending a lot of time for the reallocation of all the n keys, but I'm only getting an array that is n plus 2 larger and not twice as large. It's very easy to show that it's very inefficient. Right? If I'm just adding 2 cells at each operation, I didn't gain anything. At this point, somebody should ask, why don't I use dynamic arrays? Java supports dynamic arrays. Why don't I just let the table increase dynamically? Well, it's depending how much you care about performances. There is no, it's a unicorn. There is no such thing as dynamic array. Memory is not allocated dynamically. What Java is fooling you to think is that it increases the size dynamically, while what it really does is actually storing a few other data structures that either split the array or allocate and shift pieces of arrays. So to the user, to the programmer, it looks like it's contiguous way. However, if you really want fast enough program, you do need to allocate a contiguous space of allocation. Your program is much faster if your whole hash table sits contiguously in the memory. And in this case, and this is of course working only if you're doing it statically. There is no such thing as dynamic memory allocation for real. Okay. So so far the message was we'll try to keep the m, the number of cells, and n, the number of keys, in the same range. They need to be one at most constant away from the other. Okay, let's talk a bit about which hash functions to choose. I hope. Maybe before that, Udi Manber. There is a very, very smart gentleman named Udi Manber. He used to be until 2000, he was a member of our department, University of Arizona, at which point Yahoo, which was dominating the search, the internet search, was offering him a job to be their chief scientist and or chief research investigator. After that, he moved to Amazon to be one of the CEO. After that, he moved to Google, and right now, I think last time I checked, he was in charge of the research of everything with, I think, with YouTube. Last I checked, and he was one that developed. The very first internet searches, was really one of the pioneers. Very successful, very influential person. And I heard an invited lecture that he gave in one of the conferences. And at the end of the lecture, one of the attendants asked him what data structures, now when you're a big shot at Google, what is the one most important data structure that we have to teach our students? And his answer was, without thinking, his answer was hash function, hash table. So I don't feel too bad about teaching you things that you already saw in 345. By the way, he gave a talk in our department several years ago, and at this point, I asked him if his answer will still be the same answer, that it's the most important. And he said, yes, it's still hash function, maybe Bloom filters as well. So I'll also show you some Bloom filters, which are very much correlated to hash tables out there. It's one of the applications of hash tables that I'm planning to show you. Bloom filters. At the meantime, how do I choose a good hash function? To start with, one thing that I want is that if I have two keys, K1 and K2, and let's say they are different keys. And what I hope is that if the difference between them happens in any bit, no matter if it's the first bit or the second bit or where in the number it happens, as long as I have two keys, then I want to have a good chance that they'll map into a different cells. Now, remember, you don't know what are the keys ahead of time. The power of the hash table comes because it's dynamic data structure. First you're implementing the hash function, the hash table, and then students start appearing and you have to insert them. So you don't know what are the keys ahead of time. You do know from which universe they are coming from, say numbers with 16 digits. But you'd like to hope that the hash function that you pick is such that if there is a difference in any of the digits of their keys, then they'll map to different cells. And of course, it will always be the case that there will be students that will map to the same cells. As I said, collisions will always happen. But I would hope that no matter where the difference in the keys are, I hope that the chances that there is a collision is quite low. So let's look at the hash function that we used in the cubby over here, which was k modulo 100. Does it satisfy this desired property? Does the function k mod 100 satisfies it? But obviously not. It looks only on the first two digits, on the last two digits, on the least significant two digits. So you don't look at anything but the last two digits. So students that are different that have the same two digits but are different in different digits, the function will never notice it. Is this a bad thing necessarily? Well, maybe yes, maybe no. Here you need to know more about how the data is distributed. If the numbers of the ID are just given based on first come, first go, 1, 2, 3, 4, 5, 10, 1, 2, 3, 4, 5, 10, then probably it's not a problem. You still have nice distribution of the numbers. If on the other hand, the last digit is some control number that say it's 5 or 0, depending if you came on this year or this year, then of course it's a terrible distribution out there, and you better know, once you notice it, probably you want to pick a different hash function. However, if you don't know anything about the data, maybe looking at k mod 100 is a bad idea. Similarly, look at k mod 1024. Age of k equal k mod 1024. It has some nice properties to this function, but it also looks only at the first few digits, the last 10 digits in binary representation. Maybe it's still fine, maybe it's not, but you're only looking at the last 10 digits in the binary representation, and the function is not sensitive to see differences in other digits. How would you implement k mod 1024 in C? Actually, also in most languages, in Java as well. I'm not sure about Python, how it's done. What's the most efficient way to implement this function? You can use operation mod directly. You have it in C, you have it in Java, just use percentage, but you can do it quicker. How? Anybody? It's a hacking question. What's the quickest way in C to implement k mod? I want to do k mod, let's do it modulo 8. Actually, any number which is a power of I. K mod 8, K mod 16, K mod. How would you do it? Anybody?
Would you bit shift towards the left until there's only the remaining digits that are required for that?
I want bit arithmetic, that's correct. But so if I want k mod 8, it means that if my number in binary, if k is 1, 1, 0, 1, 0, 1, 0, 1. What do I want? K mod 8. What do I want from this number? Which digit do I want from this number if I want to do k modulo 8?
The lower three digits.
The last 3 digits. These are the only ones that I care for. Correct? If I would do k modulo 2, that is asking if the number is odd or even, I'm just looking at the very last digit. K modulo 8, I'm looking at the digit of 2 to the 0, 2 to the 1, 2 to the 2, and this gives me the number which will be some number between 0, 1, all the way up to 7, which is 111. Correct? So I only care for these 3 numbers, and I want the rest of the number to be zeroed. So which operation? People, you're after... Say again?
And 7.
I can do it mod... correct. I'm asking if I want to be extra efficient and want to use bit arithmetic, what it has a name. I assume you guys are after 3, what is this, 320 something? You're after C. You're right. Correct. And what's the name of this operation? Anybody? Just to see if you studied it. If the masking, yeah. You're using bit arithmetic, which is the ampersand operation of this number, also known as 7, and operation with k, and this gives you k mod 8. Okay, and k mod 1024 is just bit masking with, now you'll take, instead of 3, you'll take 10 or 9 such ones. Okay, so that's just a way to implement it really quickly. So let's think a bit more about this operation. Assuming that all the keys are integers and you still like the mod operation because it usually works well, then as we said, at least don't pick m to be a small divisor of some number d. It is hopeful if you're assuming that basically you'll say if you pick m such that it is not a power of 2 or not a power of 10. On the other hand, it's very convenient to pick a number of 2 because it's convenient to pick arrays that are a power of 2. So it goes both ways, but then you have higher chance of a collision. So for memory management, it's better to take m to be a power of 2. M, which is of size 2024, is great for memory management because usually we are managing blocks of memory which are sizes of power of 2. On the other hand, then you don't look at some of the digits out there. So what should you do if you only care about collision and you want to use this hash function? Then at least the safest, pick m to be a prime number. Then you actually look at many more digits out there. Okay, then you're minimizing, but then you cannot do bit masking anymore. So not everything have not everything is always good or always bad. Deal with it. Okay, once again, if m is 2 to the r and the hash function doesn't even drop, then the hash function doesn't even look at all the bits except all the first k bits. Okay, then age of k, if we want km to be 2 to the r, that's the function that we're using. We are only looking at the few rightmost bits. Okay, and the other, so two keys that are different in other digits will collide for sure. Okay, we are repeating ourselves. We are picking m to be a prime, not too close to a power of 2 or power of 10, has some pluses, had some minuses, less efficient. Memory-wise, you are using more memory, but you are safer in terms of the other m. Other option, use the multiplication method. What is a multiplication method? Pick a constant a, and this constant is, maybe I need to remind you here, hashing. A good hashing, you want to take the tofu, in my case, I'm vegetarian, take the tofu, mash it, cut it, scramble it. The more scrambled, the strangest you did, the better the better the hashing operation is. Same, pick a constant, but now you want a constant that has a lot of different digits. For example, pick your constant to be square root of 2. Okay, or a equal, I think it's 1.7 something something something. And now what is your hash function should be? Pay attention. I take k is an integer, the key of the student is an integer. I multiply it by this very strange number with a lot of digits, and I'll take the ceiling, because right now this number is float, it has a lot of numbers outside the digits, and now I'll multiply it by some number m prime, do all of it modulo m, so that at the end I'll have an index between 0 and m, and that's how I do. Why did I multiply by this strange m? Because what I actually want is that to have some way of each digit of the key to have some effect. It is even the rightmost digit of the key, once you multiply it, the leftmost digit of the key, the most significant one, will have an effect because it will multiply by something in a far away from the decimal point. Why do I multiply it by mod m at the end? Because I always need an index of the table. The table is of size m. It starts at 0, it ends at m minus 1. So this operation will give me a legit index. Let's see a bit further how it works. I'll take a, this time I'll take a that is integer, and I'll multiply by this number k, and I want to show you a slightly different method now. I'll take a, some constant, strange constant, integer, I'll take k, and here is what happened to the multiplication. You are getting a number, pretty large one, a lot of binary digits, and what should I take as the key? I need to take an index to the table. If I look at the last 3 digits, let's say that I need 3 digits. My table is of size 8, so I need 3 digits because I want a number between 0 and 7. Let's think, if I'll take only the last 3 digits, that is do modulo 8, what happens then? Look at k. What is the effect of the very first digit of k on this multiplication? You remember from 4th grade, 5th grade, when you study how to do long multiplication? What is when you're doing long multiplication, where the rightmost digit appeared? It will appear way to your left, completely to the left side. the last digit, if you change it, will change something in the result over here, but it will not change anything in the beginning of the digit that you took. Similarly, if you only change the last digit of k, that is, you have two keys that are different from each other, only in the last digit, you're only controlling this digit over here at the end. So out of all this stream of digits, which one is the best to take? Take the ones at the middle. You take the ones at the middle of the operation. So you take AK, and now you need some fast operation which will isolate 3 digits at the end, and the other rationale to think about why A times K makes sense, no matter if K is integer or K is a float. Let's think about the modulo operation. Modulo operation, how do I do plus or multiplication modulo m? I'm counting 0, 1, 2, 3, 4, all the way up to 7, and then the next number, if I'm increment by 1, will be 0, 1, 2, 3, 4, 5, 7, and so on and so forth. That's how I do modulo. Let's think about the number let's think about the number age of 1, which in this function would be 1 times a, all of it modulo 8. So this number 1 times a is nothing but a, and you fall in some location in the table. And now I want to ask, where will the number age of 2, which in this formula it is 2 times a modulo 8. And what do I hope my hash function to do? I want my hash function to say the two keys k equal 1 and k equal 2, they are different. So even though they are close to each other, I want them to fall in different locations in the hash table, far, far away, unrelated to each other. And indeed, if I look at where is 2 times a, it took me to some quite arbitrary, quite random, remember hashing with flipping, quite random locations. It doesn't depend very much on where did a was. It took me to 2a, which is very different location in the table. I'll move now to 3 times a. 3 times a takes me to yet, and of course modulo 8 takes me to yet another location far, far away from the first location, or at least not so much related to them, not necessarily close. I don't like clustering of a lot of keys in the same place and leaving a lot of keys in the same. I want to have this operation of like sprinkling keys into the table to be as good as if I'm sprinkling these keys at random. Each cell of the table has a good chance to be hit by A, which now also tells you why did I pick A to be such a strange number? Like, what happens if I take K to be an even, if I take A to be an even number? Let's think about a hash table that will be age of K to be K times 4, all of this modulo 16. Is this a good function, bad function? What do you think?
Anything even numbers, even all the odds of even thing.
No matter what is k here, which numbers will I get in the table? I'll either get all the numbers that I'll get will be 4. It will be even. No matter what is k, as long as k is integer, then k times a will be an even number, meaning that the cell 0, 0, 0, 2, 0, 0, 0, 2, 0, 4, 0, 8, all the odd cells, I'll never get to them. Actually, sorry, in this one, no. 0, 1, 0, 3, 0, 5, and so on, they'll never be hit. I'll never store anything in these cells, and then meaning that the other cells, the event cells, now needs to collect all the keys in them. You have your search time will be much higher because all the keys are concentrated in them. K equal A equal 4 in this example is even worse because now whom do I hit? I hit only the cells which are what? Only the cells which are a multiplication of 4. So you're using only 25% of the cells, and 75% of the cells are never hit, meaning that the search time is now doubled by 4. So that's why we like strange numbers, which are either floats, or going back further, we will use, I don't remember if in this deck I deleted it or not. In this number, you will even use only a few of the digits. You essentially use shift operation and modulo operation to just take a few digits at the middle. You're doing it using arithmetic shift and arithmetic modulo to just use the middle of the paper. Okay, I cannot give you bonus point for the following question, but I'm still curious who understands the references point. Where is the reference coming from?
Silicon Valley.
Very good. So indeed, well, let's see how we can use similar ideas. Here I'm diverging from the book, by the way. Here I'm how can I use hash function as a way to get redundance? Not to store data immediately, but to get some robustness, some reliable of the data. And the idea is let's store the data in a lot of places. Meaning, let's think about several hard drives. Maybe all these 8 hard drives are all in my own computer, or maybe these are 8 different users that are all sprinkled on some distributed on all over the internet. If you think about Casa in its very first days, or think about lots of more legal distributed databases, you want that the same item of data, the same key, you want to have several users that are storing it. What else do you want from it? You want, when I'll ask you, again, going back to Casa, do you happen to have my favorite song? Do you happen to have it on your computer? You should be able to retrieve it, or to tell me what is a IP of the users that might have it on their computers. What else do I want for my hash functions to tell me right now? I don't want each user to store each one of all the songs that I'm going to store. Again, I want the same song to be stored for a few different users, but I don't want each one of the users to store all the songs. Makes sense, right? I don't assume that each user can contribute a few hundreds of megabytes for my storage, and I have a large number of users, 8 on these numbers, and I don't need to store, and it's unfair to each user to say that each user will have to store the whole databases. I want to split somehow the databases between the users, but at the same time, I don't know what is the databases ahead of it. I don't know what the songs are going to be, what the keys are going to be, and I still want robustness. I want every song to be stored on several users. All these conditions make sense? I'm not going to have one read I don't need one read to be allocated to all the songs. I want to split the songs between different hard drives, but I still want every songs to be stored on 2, 3, 4 hard drives. So hopefully one of them will be awake and available and not crashed once I need my data. And all of it I want to do in distributed way without one server, one controller that decide who stored what. How do I get all of it at the same time? What I'll do is I'll decide that I'm using 3 hash functions. How do I get 3 hash functions? I'll pick 3 constants, AIs that you have seen before, instead of using always the same constant. I'll pick 3 different constants. One I'll use for the first function that I'll call age1. The other one I'll use in the second hash function that I'll call age2. Another one for age3. And this just tells me at which of the 8 hard drives a song will be stored. That is, if I have 8 users or 8 hard drives on my very own RAID, I'll decide that out of these 8, I'll store the song in the ones that are this gives me a number of hard drive, this gives me the number of hard drive, this gives me the number of hard drive, and that's where I store this song. So one song will store in 3 hard drive. And what do I get back? Now you're telling me what is K and ask, does anybody store it? And I immediately know if somebody store it, it must be either the first RAID, what I can compute what is age1 because I know the hash function, and so is every user on the system. Each one knows what is age1, so you know at which what is a first choice or second or third choice of where do you store these songs. Now, if your hash function is good, then each one of these 3 numbers is uniformly random. They might have some collisions, but they're uniformly random. So if you are storing 1,000 songs, then each one of the hard drive will have a more or less the same share of the songs. So once again, you're hoping that every cell will only have the 500 homeworks divided by 100 cells, only about 5. It will be as if it is randomly distributed. If you have 3,000 songs, you want to store every song 3 times out of 8 cells, then it will be the 3,000, so 3,000 songs times 3 copies that I want each one to store. All of it divided by 8, that would be the average number of songs that each one will have. So it's completely fair. Everybody needs to store more or less the same thing. And if the number of hard drive is larger, then of course this number is smaller and smaller. You have robustness, and mostly out of these 3 numbers, hopefully one of them did not crash. Okay, and is awake and online when I need to pick this song or this data item. Make sense? So that's how several hash functions help me tremendously when I organized either distributed database or I have one big memory with a lot of hard drive, but I'm afraid that some of them will be crashed. I am storing several copies of the same song, but which of the hard drive do I pick for each copy? That's exactly what the hash functions will be. And I assume that that's the algorithm that whomever was consulting Silicon Valley had in mind. And insert and delete and find all works very, very efficiently. So what was a big idea that we added on the single hash function? That now if we can generate 1 hash function, then we can generate 3 of them, and suddenly we got all the desired properties all at once. I'll talk more about this example at the beginning of next class. We'll also do a bit active learning of stuff that we discovered, that we studied so far. Any questions? Okay, very nice. Thank you. First time well, ending just in time.